Hello everyone. Write down wave optics. And there are two types of optics which we study. One is ray. Ray optics means reflection, refraction. In reflection and refraction, you know that we are considering straight line motion, rectilinear motion of light or light ray. We don't have to worry about internal mechanism of the process which deals with propagation of light. We're not that much interested in ray optics and that part, but what light is basically, fundamentally, this is something which needs study of wave optics. Now, from electromagnetic waves, we already know that light is an electromagnetic wave, which means it has two components. One is electric field component and the other one is magnetic field component. Now, let me ask you a simple question first. What do you think is the important component out of this electric field and magnetic field? What is that component which makes us see all the things? When you look at this marker, when you look at me, and you look at the board, light is coming from the board and is reaching your eyes. So when I say that light is reaching your eyes, what is that component which is basically interacting and producing this sensation which you call image formation? Can anyone answer this? And this is something which needs everything which we have already done in electrostatics and magnetic field. Let me answer this. Some of you are answering. Good, that's the correct thing. Third answer is correct. It's the electric field component. Why? Because you know that magnetic field does no work. So when magnetic field component of light interacts with your eyes at the retina, the electrons which are present at retina, those electrons, when they interact with magnetic field, if charge is at rest, then magnetic field can exert no force. You know that. And therefore we say that magnetic field does no work. So what is the component which is responsible for seeing things? Electric field. What is the force of electric field? QE. It has nothing to do with charge being at rest or in motion. So write down this first statement. The component of light which interacts with electrons of our eyes and does some useful work is electric field component. Therefore, when we see things, it is possible because of electric field component. It is possible because of electric field component. Inside bracket, magnetic field component is useless as it does no work. Magnetic field component is useless as it does no work. So, in wave optics, we'll be dealing with this electric field component of light. And we have done elementary part of this wave optics in 11th itself, like propagation of wave, equation of a wave, meaning of wavelength and all these things. This is something which we already done in 11th. I will discuss a little bit about the basics of these things. But if anybody is interested in deep analysis, you can request for a lecture of 11th and I'll give it to you. Right now, the thing we are interested in is E, which is E naught sine omega t minus kx. We have seen this thing in electromagnetic waves. The same electric field is present in front of you. This is E naught sine omega t minus x upon v. What is k? You know that. K is omega upon v. Take the omega part inside, which is basically 2 pi upon lambda. We have already done this much in electromagnetic waves. But let's understand meaning of this. If I simply give you the equation part as E equals to E naught sine omega t minus kx, then it will be too mathematical for you to visualize everything. But if you can graphically understand this, meaning of E, meaning of t, meaning of x, if you can understand this, this chapter wave optics will be very easy for you. Otherwise, you will find that there is too much maths involved. So, let's start with this E, because this E is something which helps us in seeing everything around us. If I plot a graph of E versus t, this is the shape at x equals to 0. Pay attention to each and everything. This is E naught. Let's see how much you know from 11th. What is this length called? What is this length called? Write down this in the comment box. And it will keep you active also. Try to interact What is this length called? Only two have responded. Others, as usual, are forget it. Now, those who have answered, they are answering that this is wavelength, and that's the reason I asked you this. This is not wavelength. What do you write at this place? Capital T. Now you will remember always that this is not wavelength always. When does it become wavelength? This shape, we'll see that. Look here. At x equals to 0. Look at this. If in this equation you put x 0, then you get what? E naught sine omega t. At x equals to 0, E is E naught sine omega t. And how do you draw the graph of sine? This is the graph of sine. What is written at this place? T by 2. What is this length? This whole length is capital T. It's not wavelength. Now, let's draw this graph again. E versus X. E versus X, and say we are drawing the graph at t equals to 0. At t equals to 0. If I say I am drawing the graph at t equals to 0, look at this equation. Put t equals to 0, it becomes what? E naught sine minus of kx, which is simply E equals to minus of E naught sine kx. Put t equals to 0, you get what? Minus of kx, and you can take the negative sign out. E equals to minus of E naught sine kx. How do you draw graph of sine with a negative sign? Graph of sine with a negative sign. That's how you draw the graph. Now if I ask you, what is this length? Then your previous answer will be correct. This length is lambda or wavelength. This is lambda. This is lambda. This is lambda by 2. Now, if we can understand meaning of this and this, then only we can understand wave optics. There are things like interference, diffraction, all these things, you will understand them provided you deeply understand each and every part present in this and this. Now, let's try to answer this second question. Which length is greater, this or this? if I draw a graph like this and if I draw a graph like this, then which one should have larger length? Can you answer this? And this is something which is taught in 11th, the very first chapter, units and dimensions. And what are you taught? You cannot compare time, seconds, with length, meters. Which means you don't have to draw these graphs of exactly same length. In the second graph, horizontal axis represents what? Position, meters. Whereas in the first graph, horizontal axis represents time. What you can compare is this peak. This is no doubt E naught, because on the vertical axis in both graphs we are plotting what? E. So what basically is the difference between first and second? We'll write that, but before that, note down each and everything exactly like this. Note down this much. So all those who are writing that the lengths are same, I hope they understand that you cannot compare these lengths. One length represents time period and the other length represents wavelength. And much more about it, but first note down this much. Now look, first graph, it gives you values of E at a given position. It can be x equals to 0, it can be x equals to 1, 2 or anything. At a given position at different times, what are the values of electric field? This is given by first graph. Right at this place, suppose this is the x equals to 0 position. At this place electric field is 0. Then it increases, it becomes maximum. It becomes maximum after what time? After a time of t by 4. So in the beginning it was 0, and then just look at this level of my fingers. This represents 0 electric field, and then it increases, and after t by 4 becomes maximum. Another t by 4, it becomes 0. Another t by 4, it reverses direction and now increases in this direction. another t by 4, it becomes what? 0. At a given position, the way electric field changes its values is given by first graph. Write down this. Call it graph 1. And call this graph 2. Now write down the statement. In graph 1, magnitude and direction of electric field is shown at different times, but at a given position. That position doesn't necessarily be x equals to 0 always. It can be x 0, 0.1, 0.111111. All the positions are there. But at x equals to 0, if I ask you to plot it, that's how you get it. Now, what is graph 2? Graph 2 is telling you that this is x, this is lambda by 2, this is lambda, this place will be lambda by 4, this place will be lambda by 4, this place is x equals to 0, which is this. Now, let's understand this graph 2. In this graph, at a given time, at t equals to 0, if you look at different positions, if you look at these different positions at the same time, then what you found, at x equals to 0, electric field was 0. At x equals to lambda by 4, electric field was maximum, but in the negative direction. At x equals to lambda by 2, electric field is 0. At x equals to 3 lambda by 4, electric field is maximum in the positive direction. At x equals to lambda, electric field is again what? 0. So what is this graph? This is x equals to 0 position. X equals to 0. Right at this place, electric field is 0. Look at the tip. Electric field, remember, is 0. At a distance of lambda by 4, what do you notice? That electric field is maximum, but is in the opposite direction, negative direction. This much gap is what? Lambda by 4. Right here, there is no electric field. When you move to x equals to lambda by 2, electric field is again what? 0. At 3 lambda by 4, electric field is maximum and is in the positive direction. At x equals to lambda, it is again what? 0. This second graph, it gives you its strength and direction of electric field at a given instant, but at different positions. Write down this. In graph 2, strength and direction of electric field. In graph 2, strength and direction of electric field is shown at a given time instant, but at different positions, but at different positions. Now let's add one more thing. Right at this place, electric field is zero. Let me ask you first. Let's see how much you understand this graph and this graph now. At t equals to 0, electric field at this place is 0. That means after t equals to 0, electric field, it's going to change. It is 0 right now, but just after dt time, it will have different value. That different value will be in the positive direction, or will it be in the negative direction? What do you think? Answer this. At this place, at t equals to 0, you found that field is 0. Just after t0, what do you expect? Electric field to rise up in the positive direction, or it will be in the negative direction? What do you think? Positive or negative? Answer this in the comment box. If you think positive, then write down positive. If you think negative, then write down negative. The only one answer is correct. Take help from this. At x equals to 0. Where? Right here. At x equals to 0, when time is 0. What is electric field? 0. As time increases, electric field is in the positive direction. So at this place, if you look after some time, electric field will be in the positive direction. Look at this place. Electric field is 0. What is this place? This place is at a distance of lambda by 2. And do you know what is the meaning of lambda by 2? I hope you remember phase difference. Phase difference between this position and this position, lambda by 2, is 180. What is 180? If this is up, then this will be down. That means after some time, if you look at this place, you will find that electric field is pointing downwards. Electric field is pointing up. Electric field is pointing up. And how is this going to help us will depend very much and decide everything for your wave optics part. And therefore pay attention. Look here. This second graph. What is the meaning of second graph, and how do you understand the meaning of E changing at different positions is something which is going to help us in understanding wave optics. Look, electric field is 0. Dot will show the value of electric field. Electric field is up to this point. This is electric field. Electric field is 0. Electric field is up to this point. Electric field is 0. Electric field at different places. After some time, what will happen? Right here, electric field will be up to this point. At this place, at this place, at this place, at this place, now do you understand what all you see in this third figure? Look at this shape. And now again look at this shape shown in blue. I hope you can see that wave is propagating in this direction. Look here. Look at this black shape. And then it reaches this position. Wave is propagating in this direction. This is at t equals to 0. This is at when time is dt. Let's say after 1 second. You can say dt, you can say 1 second. Don't get confused with dt. Just for your understanding, let me say that this time is 1 second. After 1 second, this will be the shape. So what are these shapes? What are these shapes? These shapes are all electric fields at different positions. Look. The thing which you see in black graph is what? These arrows. Electric field is up to this point, up to this, and then decreases, changes direction, and so on. At x equals to 0, electric field is 0. Lambda by 4, it is maximum in the negative direction. Before lambda by 4, it is not maximum, but is something and is in the negative direction. After lambda by 2, it changes direction, and at different points you can see the strength. Up, 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 up is maximum at 3 lambda by 4. 3 lambda by 4. So when you see this shape, it is basically what? It is giving you tips of these arrows. Connect the tips of these electric field arrows and you get this black graph. Now, this was at t equals to 0. If I ask you to draw the same thing at t equals to 1 second, then what do you notice? This thing, electric field at this place was 0. And after some time, electric field at this place will be in the positive direction. Why? After some time, electric field at x equals to 0 is increasing in the positive direction. So after 1 second, if you look at this, I will not draw in the same figure because it will complicate the thing. You can understand this. And now, right here, you see what changes in the electric field. This electric field, let me draw these arrows in this figure. This is the shape of arrows, blue arrow. Connect the tips and you get structure at t equals to 1 second. Now, this is maximum. At this place, electric field has to decrease now. And therefore, you can see that the black arrow was up to this point. And now it has come back to this position. I hope you can see the movement of fingers. It was up to this point and now it has moved to this position. It was up to this point and now it has decreased to this position. At different places, electric field is continuously changing with a time period of capital T. Position tells us this. Time tells us this. Now again, this helps us in understanding wave. We'll see that draw this much, and if you understand complete meaning of E versus T and E versus X, then write down yes in the comment box. Now, why do we need this much knowledge about electric field and its variation with time and position? Your eyes, let's say, are placed at x equals to 0. Light is coming, and at x equals to 0, assume that you have your eye present. So your eye is going to see this variation, which means what? At t equals to 0, your eye will find that electric field. At t equals to 0, your eye will find that electric field is what? 0. At t equals to t by 4, your eye is going to say that electric field is maximum at t equals t by 2, electric field is 0, 3t by 4 maximum, capital T 0. But do you know what is the order of capital T? Is there anyone who can get an estimate of capital T? What is the order of capital T? What is this time duration roughly? Anyone, can you answer this in the comment box? Any idea about the order of capital T? Rough idea. Nobody. Look. Everyone has seen this relationship, V equals to F lambda. V equals to F lambda. Speed of light is 3 into 10 to the power 8. Frequency is 1 upon T. Lambda, I hope you know that for yellow it is around 5000 angstroms. Let's write down 5000. Angstroms means 10 to the power minus 10. What is this? It is giving you T as 5. Look, 10 to the power minus 7, and this is 10 to the power 8. Denominator, numerator, you get 5 upon 3 into 10 to the power minus 15 seconds. 10 to the power minus 15 seconds. Let's take a wavelength of 6000. This is 6, and the time is coming roughly 2 into 10 to the power minus 15 seconds. For a wavelength of 6000 angstroms, your time is coming 10 to the power minus 15 seconds. Minus 15. What is minus 15? Minus 15 means starting from E0, becoming maximum, becoming 0, becoming maximum in the opposite direction, and again becoming 0. One oscillation is complete in what time? 10 to the power minus 15, which is very, 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 very small. And therefore, your eyes, or you can say your brain, cannot measure this type of fluctuation. You will not see zero field, you will not see maximum, you will not see 0, you will not see maximum, you will not see 0. This is something which is beyond the capability of our brain, because variations are taking place in this much time. Or you can understand this way: if this is T, then what is frequency? Roughly, let's make 1 upon 10 to the power 15. Just the order part. 1 upon T, it becomes what? 10 to the power 15, roughly. What is 10 to the power 15? 10 to the power 15 oscillations per second. That's the meaning of frequency. Which means this type of curve, how many these curves? These many. 10 to the power 15 in 1 second will be observed by your brain, which is something completely beyond the ability of human beings or anybody. Then what do we see? What is the energy which we are going to observe? That energy is called intensity. Our brain, instead of measuring these instantaneous values, measures what? Intensity, and this intensity, is proportional to amplitude square, which in this case is E naught square. So brain is not going to measure 0, maximum 0, things like this. It is only going to see what? Average intensity. What is average intensity? It's coming proportional to E naught square. This is something which you have seen in alternating current. In alternating current, you have already seen this type of thing, I naught sine omega t. And then we measured average power. If you remember, average power was what? ERMS, IRMS cos phi. So what is ERMS? E naught. IRMS, that is also E naught upon R. E naught, E naught. Directly we can get it from that alternating current part. But remember that intensity is proportional to what? Amplitude square, which in this case is E naught square. So our brain measures what? This E naught and its square. This is the heat, energy which is being transferred. Average heat, average intensity, average energy which is being transferred to your eyes by an incoming light ray. Because you cannot see these instantaneous values. And then what? For different colors, this time gap is different. Vividor, violet, indigo, blue, green, yellow, orange, red. For these, this variation is going to change. Blue will take a different time to complete one oscillation. Yellow will take a different time to complete one oscillation. Green will take a different time to complete one oscillation. Now, depending on the time which it takes to complete one oscillation, your brain is going to perceive that variation in electric field as a color. It's like this. It's not the color and then the variation. It's the variation and then the color, which means, just for the time being, understand this way. If suppose electric field changes in 10 seconds, remember, this is the order, just for understanding. If electric field changes in 10 seconds, you will call it blue. If electric field changes in 2 seconds, you will call it green. If electric field changes in 1 second, you will call it a different color. So, frequency of electric field variation decides perception of that electric field in the form of color. So your eyes are receiving what? Energy. Your eyes are receiving what? Energy of an electromagnetic wave. But the way your brain perceives that energy is in the form of a color. Now, for a given color, say red color, if you find that red color is this, then look at this interesting thing now. If your brain, let's say, says that this is red color, then for your brain, this is also red. this is red, this is also red, because you can see that frequency is what? Same. Variation of E with T is same. But what is intensity? Proportional to amplitude square. Look at the amplitudes. Say this much is 2 E naught. Then your brain is going to say this is red, this is also red, but this is more intense red. Brightness of this red is very much as compared to this red. Frequencies are same color, but this is going to give you more heat, which will be interpreted by our brain in the form of what? More redness. If I change the frequency, I will totally change the perception. Now that thing will become from red to blue or some other color. But the thing is, intensity, it depends on what? Amplitude. And perception of color, it depends upon what? Frequency. These are the two things which your brain observes all the time. In wave optics, what we are going to do, if we can completely remove this, if we can make electric field zero, if we can make E naught zero at some place, then you are going to see what? Complete darkness. We'll call it destructive interference. On the other hand, if at some other place we can increase the amplitude, then brightness of a color will increase, which will be called constructive interference. This is what is going to be discussed in this wave optics part, and is all coming from this much analysis of sine curve. If you understand meaning of sine curve, intensity, brightness, perception of color and all, then write down yes in the comment box, and then we'll write few statements also. Write down statement. Frequency of light decides its color, whereas amplitude of electric field decides brightness of the color. Amplitude of light or amplitude of electric field decides brightness of the color. Let's draw this thing in a systematic way. Let's see you can answer this or not. Vidgear. Which one has a greater frequency? Violet or red? Answer this. Only one person would answer correctly. When you move in this direction, frequency increases. When you move in this direction, energy increases. Remember this. This will help you in remembering this. And what is energy? I hope you have seen this formula H nu, energy of a photon. This nu is nothing but F. For simplicity, the frequency part. Energy of photon is what? H nu or HF. H is Planck's constant. So when you move from red to violet, energy increases. Now can you remember this simple statement? When you start heating an object or a metal, you can say, initially it will be red. If you continue heating this rod, its temperature will become orange, yellow, green, blue, and at very high temperature, it will be giving you what? Violet. Normally people think that red, hot. In normal conditions, when you start heating an object, it becomes red. Red means red hot. But continue increasing the temperature and you will see these colors. If you have seen those bulbs with filaments and all, the old bulbs, at very low voltage, they look reddish. At normal voltage, they look yellowish. If you increase the voltage and the bulb filament is about to fuse, it becomes almost bluish or violet type. So remember, as you increase the voltage, as you increase the temperature, as you give more energy, that's how colors change. So it will help you in remembering that in this direction frequency increases, in this direction your energy increases. And therefore, if you move in this direction, T will increase. Time period. Frequency is 1 upon T. That means a very elementary question which you can expect is of this type. graph A, graph B. We have been told that one of these is for red and the other one is for blue. Which one is for red and which one is for blue? Answer this in the comment box first. You cannot expect anything easier than this. If you cannot answer this, then you yourself decide we can do. Everything is on the board. Which one is red and which one is blue? Only one person has answered so far. Is it too much to ask these questions? And do you find that even this thing is difficult? Second response. I'm asking red and blue. So answer between red and blue only. Only two responses. Third, fourth, fifth. 5 responses so far. Everything is on the board. There are still 3, 4 who could not answer a single thing. Means what we can expect from you if you cannot answer something like this. Everything is on the board. As I increase time, I will be moving for red. More T means red. Which one has greater time period? This one. And therefore A is red, B is blue. You can expect simple questions like these. More time period, less frequency, less energy. Less time period, more the frequency, more is the energy. Now, if somebody decides to draw a graph like this, A, B, this is graph C. What is the color of graph C? What is the color of graph C? And what is different in graph C? Answer that in the comment box fast. If somebody asks you to compare graph C with all the other ones, then what will you answer? But definitely amplitude is different, but what are you going to see? Good, that's the answer. The C is also red, but less bright. graph C, it does represent red color because you get same frequency, same time period, but since its amplitude is less, it will give you less brightness. And same thing you can do here also. If somebody decides to plot a graph like this, and let's call it graph D, then I hope you understand now that D is blue. But you can see the amplitude, I have increased the amplitude part. Intensity is proportional to amplitude, and therefore this is more intense blue, dark blue, you can say that, or you can say that brightness is more. More brightness. Kind of, you can understand like this. You have a blue light source, you have 10 blue light sources, suppose. You switch on one, you switch on the other one, second, third, fourth, fifth. As you keep on switching these bulbs, you will find that intensity of blue color is increasing. So what you are doing, you're not changing the frequency, you're only changing what amplitude. And in this case, you're basically switching off these bulbs one by one. Initially you had 10 bulbs on, now you have got only, let's say, 2 bulbs on. 10 red bulbs on, more redness. 2 bulbs on, brightness has decreased. In interference, which we study in wave optics, our aim is what? Now you will be able to understand that, and we'll complete this thing in the next lecture. At a given place, if I can increase the amplitude, then intensity of color will increase. This is called constructive interference. How can you observe that? Very simple part. Let's say you have a light bulb, and on this light bulb you superimpose light coming from a second bulb which is exactly in the same phase, same type of variation. Then these two, after superposition, will give you what? More brightness. This will be called constructive interference. And suppose this light wave is superimposed over this light wave, up and down, they will cancel each other, or partial cancellation or complete cancellation. If you get complete cancellation at a given position, no electric field is present, that means no work is being done by the electric field at the retina, and therefore you do not observe anything. Complete darkness, which will be called destructive interference. We'll see this in these two types of interferences in the next lecture. Note down this much and then you can leave. Thank you very much.